Hey everyone, welcome back to Ingis Education. It's been a while since my last video, but I am excited to be back with a more systematic approach to create educational content on engineering. This new format is designed to boost productivity for both myself and my audience. From now on, I will focus on different engineering modules commonly taught at undergrad BSc engineering courses at top universities. We will start with the most common modules and then dive into more specialized ones unique to various engineering fields. So, what exactly is engineering design principles? In this course, students dive deep into three main areas. Number one, the design process. Number two, material selection. And number three, prototyping techniques. In this video, I have incorporated example project of all three areas. For design process, I have designed a DC motor controller board. For material selection, I have designed a robotic arm and discussed the suitable materials for the component. Prototyping techniques are also discussed in the Arduino buggy reverse engineering. First, let's talk about the design process. This involves several key steps. Number one, understanding and defining the problem. Clearly identify the issue you are trying to solve. Number two, developing design concepts. Brainstorm and create initial sketches or digital models of potential solutions. Number three, iterative design and testing. Build prototype, test them, gather feedback, and refine your design. Number four, project planning and management. Organize your project to ensure it stays on track within the budget. For our example today, we will reverse engineer a robotic arm manipulator. We will start by disassembling it to understand its components and how they work. Then we will take measurements and create CAD model. Finally, we will modify the design by replacing the existing servo motor with a DC motor and a stepper motor. Section 3. Material selection. Next, let's discuss material selection. Choosing the right material is crucial for the success of any engineering project. You need to consider the following. Number one, properties of material. Look at mechanical, thermal, and electrical properties. Number two, criteria for selection. Evaluate materials based on their performance requirements, such as strength, weight, and durability. Number three, cost and availability. Balance performance with cost and ensure the materials are readily available. Number four, the last but not the least, environmental impact. Consider the sustainability and environmental effects of your material choices. For instance, selecting materials for a bicycle frame involves finding materials with a high strength to weight ratio, such as carbon fiber or aluminium. This ensures the bike is both strong and lightweight. You also need to ensure the material can withstand environmental conditions and mechanical stress. Finally, you balance these factors with material cost to stay within the budget. Prototyping techniques. Lastly, let's explore prototyping techniques. Prototyping is essential for turning your design into tangible products. Common methods include: number one, rapid prototyping. Techniques like 3D printing and CNC machining will allow you to quickly create physical models of your design. Number 2, creating physical models and simulation. Build prototype to test how it fit and function in real situation. Number 3, testing and refining. Use this key prototype to gather user feedback and make necessary improvements. Number 4, documenting and presenting. Keep detailed records of your design iterations and prepare to present your findings. For example, when developing a prototype for a wearable fitness tracker, you might start by creating a CAD model. Then you could use a 3D printer to produce a physical prototype and evaluate its form and ergonomic. After conducting usability tests and gathering feedback, you'd refine and design until you achieve the final product. As a sample coursework, we will reverse engineer a robotic arm manipulator. Now let's get into our reverse engineering project. Here is how we will do it step by step. Number 1, disassembling the robotic arm. Carefully take apart the manipulator to study its components and mechanisms. Number 2, taking measurements. Measure all the parts accurately to create precise digital model. Number 3, creating a CAD model. Use Fusion 360 to plot the dimensions and build a 3D model of the manipulator. Number 4, modifying the design. Replace the existing servo motor with a DC motor and a stepper motor. Make necessary adjustments to the design. Number 4, prototyping. Use a 3D printer or CNC machine to create the modified parts. Number 6, testing and refining. Assemble the modified robotic arm, test its functionality, and refine the design based on performance. Here is our CAD model in Fusion 360. By replacing a servo motor with a DC motor and a stepper motor, we can improve the precision and control of the robotic arm. I have also made a step-by-step video how to create this CAD and then 3D print and the electronics in different video. Please explore in my channel. Now let's explore little bit more in the coursework. What kind of coursework you can expect at the universities. To give you a better idea, here are some sample coursework you might encounter in this module. Number 1, a design project. You might be asked with designing an ergonomic office chair or a bicycle frame. Following the complete design process from concept to prototype. Number 2, material analysis. Find the suitable material for your project. You could be asked to compare different materials for a specific application, considering properties, cost, and environmental impact. Number 3, prototyping assignments. You may need to create a test prototype for various products, documenting the iteration and improvement. And there you have it. The engineering design principle module covers essential skills that every engineer needs, from understanding the design process and selecting appropriate materials to mastering prototyping techniques. Now at the next part of the video, I have incorporated 3 design engineering projects. These are basically from the previous coursework I have designed, but just to make this content more researchful for a new beginner, please watch all 3 parts of the video. Let's get started. Hello and welcome to another video at Indies Tech. In this video, I will explain how you can use 555 timer to control a 12-volt 6-cable bipolar DC stepper motor. Now, as you can see on the left-hand side, this is my 12-volt bipolar DC stepper motor run by the 555 timer. Now this motor has got 6 cable and it has got 2 of the primary coil inside. This is why they are called bipolar. Now let's explain the circuit diagram. Before everything, I will explain the 555 timer signaling component first. So 555 timer has got 8 pin. As you can see from the left hand side where the circular mark started is pin number 1. Pin number 1 connected with the ground. Now pin number 2 is very important where all the clocking input happens. So whatever happens in pin number 2 affects pin number 3, generating the clocking pulse. So pin number 2 starts from the electrolytic capacitor, 0.47 microfarad capacitor I used, where the negative part of the capacitor is connected with the ground rail and the positive part is connected with pin number 2. Now between pin number 2 and pin number 7, 220 kilo ohm resistor connected in parallel configuration. Then from pin number 7 to the positive rail, another 2 kilo ohm resistor. So this is the overall pin number 2 configuration. If you get this part right, then you've done most of the things right. Now let's go back to pin number 3 where the clocking signal is generated, and as you can see, this clocking signal is directly connected to 2 of the transistor. Now I will skip this part. I will go back to stepper motor configuration. This is a 12 volt 6 cable bipolar DC stepper motor. Now the bipolar DC stepper motor has got 6 cable. As you can see, the right hand side, the green color cable are 2 ground, then other 4 cable is for 2 primary coil. Inside the DC stepper motor has got 2 primary coil, and each of the primary coil has got its own 2 secondary coil. Now one of the primary coil is responsible for clockwise movement and another primary coil is responsible for anti-clockwise movement. As I said, each of the primary coil has got its own secondary coil and they are run by 3 cable. In my design, the ground is always on. Now to run the motor for clockwise or anti-clockwise, you need to turn on the other 2 cable one after another in sequence. They can't be turned on in any given time together. They need to be turned on one after another. Let's verify the coil configuration as I have just said. So I took off the jumper cable, and as you can see, I'm just connecting one of the ground with the ground cable. For the explanation here, as you can see, I will inject the 12 volt voltage with the first green cable and the white and red cable, but obviously I need to turn them off in sequence. So for the motor to move clockwise, my design circuit need to turn the 2 of the cable, the white and red cable, one after another in sequence, and the motor will move clockwise. For anti-clockwise movement, I need to change the ground, the second ground, and the blue and yellow cable need to be turned on in sequence. Then the motor will move anti-clockwise. At any given point, only one set of coil are allowed to be turned on, otherwise the motor will heat up. Now let's go back to the project schematic. So I have already discussed till this point the clocking signal. Now let's go back to the motor itself. So this is the 2 of the primary coil. As you can see, the secondary coil has got 3 cables. So each of the primary coil has got 3 cables, and they actually put voltage to the secondary coil. So this cable is the ground. So this same color one. So the ground is connected with this in this configuration, and I put 4 switches to 2 of the secondary coil cable. So if I turn on these switches at any given time, this part of the circuit will turn on, will get the 12 volt voltage to this coil, and if I can turn on this one, it will get the voltage and the motor will move anti-clockwise. At any given time, only one set of the switches are allowed to turn on. On the other hand, the ground is always on. Now this transistor is a NPN TIP31C transistor. So it has got 3 legs: base, collector, and emitter. Base is a switch, and collector is connected with the positive rail, and emitter is connected all the way through one of the coil. So what happens is that when the clocking signal reach there. So base is the switch of the transistor. So as long as there is a voltage on the base, these two pin will get short. So this positive rail 12 volt will go to this cable. Now this one is only activated when the clocking signal is active high. Then what happens is that when this one is active high, the other cable needs to be turned off. So that way I executed this is that, look at this carefully. So these three are same transistor. So what happened is that this transistor emitter is connected with the positive rail, then collector is connected same like this one with the another of the secondary coil cable. The base, the switch is always on. As you can see, it is connected with the positive rail via the 330 ohm resistor. I try to make this circuit a little bit technical. So what happens is that this transistor is always on. So this guy is supposed to take power always, but I put an interrupter. So we all know that electricity follows the path of least resistance. So I have used another TIP31C transistor. This guy is connected with a ground. So anytime there is a voltage here, this ground will be getting on. That will prevent any voltage going to this transistor. So this coil will not get any of the power. So this transistor is switched with active high signal. So same signal is switching on this one and this one. So what happens is that when this two is on, this one provide power to this cable, but same time this one turn off this one, and there is no voltage here. So this cable is turned off, and vice versa. When there is active low, this transistor is deactivated, and this JP31C get the voltage and it can provide power to the other cable. This way, at any given time, only one of the cable can be switched on and off. So this is toggle between, and thus the two of the coil get excited one after another, and the motor moves clockwise. But here you can see I have connected the other cable in parallel configuration, but I put some switch on. So here is the switch. At any given point, one of the set of the switch should be on. So what happens is that if this part of the what happens is that they get the same clocking signal, same on and off signal in same sequence. But if you turn on this switch and turn off this switch, the motor will move clockwise. Otherwise, will happen if you turn off this setup switch and turn on this setup switch, the motor will move anti-clockwise. So I have turned off both of them. So if I turn on this setup switch, the motor will move anti-clockwise. Here you will see. It's quite difficult to turn on this match. So here you can see the motor is moving anti-clockwise. Same time, if I just switch it off, the rotation will stop. Then I will turn on this setup switch and the motor will move clockwise. So this is a simple design. You can make a integrated circuit where the whole thing will be much more neat and tidy. So hopefully I will make this in my next project. This is the end of this tutorial. So if you like this, just let me know your opinion in the comment box. Till then, I will see you at next time. Goodbye. Welcome to another video at IndieStech. This video is part of the series of the video I'm making on Raspberry Pi 4 based pick and place robot. As you can see, the robot is a Raspberry Pi 4 based omni wheel pick and place unidirectional robot, and I have used the motor controller, which is a TB661FNG from the image you can see. So I will discuss the pinout of the motor controller, how you gonna connect it with Raspberry Pi 4. In my project I have used Raspberry Pi 4, but you can use Raspberry Pi 5 as well with the same pinout configuration. Now there are different versions of TB66 motor controller. As you can see, the top one actually I have used, but the bottom one is more common. As you can see from the GPIO configuration, 4 GPIO has been used to control 2 motors at the left, then another 4 GPIO for 2 motors at the right. Now the motor are getting the power, operating power from the 9-volt battery. You can use other more powerful battery, but the TT motor only works with 6-volt and 12-volt battery. So you can use a buck converter if you want to utilize it as like a 6-volt power source. At the display you can see I have also mentioned the Python code, a bit of the Python code with the pin configuration. So basically for left side motor, as you can see, GPIO 17 is assigned for the input 1, then input 2 is GPIO 22, and then the other motor, left motor B1, is pin number 23 and 24. Same goes for right hand side motor. INA2 is pin number 6, then INA1 is pin number 13, then the other one, INB1 equal pin number 19, INB2 pin number. Now for better explanation, I have opened my FreeZing circuit simulation. FreeZing is a very visualizing way of simulating circuit. It's very simple to use and I highly recommend. Now let's go back to the pinout. First I will zoom. So these are the pinout. As you can see, left side motor connected with Raspberry Pi 4. This 4 GPIO is more crucial for this 2 motor control. So what are the pinout? So the first pin on the left is basically powering the motor control board, and this one is the VCC. So VCC is connected with the 5-volt Raspberry Pi 4 power supply. Then this pin is for ground. Ground is connected. There is a common ground with Raspberry Pi 4 GPIO. I'm saying Raspberry Pi 4, but that doesn't mean that you can't use with any of the Raspberry Pi. You can use it with Raspberry Pi 3 as well as Raspberry Pi 5. So these are the motor output. So basically the board output, which is feeding the power to the motor, AO1. So from my code at the left, the part of the code on my left, as you can see, I have named them LINA1, which is basically this pin. And the other pin is AO2 in my code, which is LINA2. L means left, IN input, A2. So these 2 pin correlates with these 2 pin code out. Same goes for these 2 pin and the common ground. Now right hand side, this is PWM. So there is only one common PWM I created from one pin from this Raspberry Pi 4. As you can see, this is GPIO 12. So from my code, I will discuss the code in next video, but for this just keep it in mind that GPIO 12 I have used to generate one common PWM, and that common PWM then shared with both the board. So as you can see, this common PWM is connected with this motor control board and this motor control board, and obviously both of them are TB6612F and G. Next pin is that input 2. So basically GPIO 22 is feeding all the way to this pin, and then this GPIO 17 is feeding this input. and this is for the standby voltage. So basically I have utilized this PWM signal. That PWM signal is putting both the board standby. Then the other input from the Raspberry Pi 4, which is connected to GPIO 23, and the next one is connected to the GPIO 18. Now if I just zoom out and go to the other side of the control, so as you can see, so it's easy to understand this bit because these are just motor control, motor signal going from the TB661 to the motor, but the control signal is coming from the Raspberry Pi 4, and for this one GPIO 26 is used, and the next one GPIO 19 has been used. Same for this one. GPIO 13, and this one goes GPIO 06. So basically this part of the signal coming from the Raspberry Pi 4, this is just only telling the motor control board how much voltage should go to these 4 motors. But the power source is actually this 9-volt battery, which is in turn using a buck converter. The buck converter is converting 9-volt to 6-volt, then 6-volt is used to run these 4 motors. In my project, I actually used NIMH more powerful battery. Those are like 36-volt battery, but I have used this same buck converter to reduce the voltage, to step down the voltage from 36-volt to 6-volt. Now another power source, 9-volt power source I have utilized in this project, that is to power the Raspberry Pi 4, because the whole circuit is used in a mobile robot platform, so the Raspberry Pi 4 requires its onboard power supply. The problem is that 3 amps, 5-volt 3 amps, the power requirement of Raspberry Pi 4 is too difficult to share one power source. That's why I have used completely a different power source only for the Raspberry Pi 4, and that is simple enough that you get a 9-volt power source or 34-volt, whatever, then you use a buck converter to generate 5-volt 3 amps. So basically this is the potentiometer. If you turn around at one point, you will get 5-volt, and you can use this one of these USB-C. This one is micro USB, but I have used USB-C. You can buy USB-C barebone connector just to connect this plus and minus output from the buck converter, then feed up with the Raspberry Pi 4 USB-C power source. That will power the Raspberry Pi 4. That's all for today. I will see you at next time. Hello and welcome to another video at Indie's Education. So finally, after all the 3D printings and CAD design, our Omni-wheel custom built chassis is ready. So in this video we will assemble this chassis and we will deploy it and see how it works. So basically this is the body originally. So as you can recognize this Arduino buggy you can buy online. So originally my idea was to reverse engineering this, because the space of keeping the microcontroller or Raspberry Pi and the batteries is really small. So I built the volume, I increased the volume, I built this adapter. As you can see, this really fit with the, so this way you get more spaces here in this place. Also structurally it become more stronger. Then you put the motor adapter and the TT motor inside. That's how this was the original idea to build the chassis. If I can just assemble all four, that would look like this. So without screwing, I'm just showing the idea. So that's how it would fasten with the main body. But then I figured out that there are more ways to increase the area volume just to get rid of this Arduino chassis altogether. So now the idea is to use this custom 3D printed extrusion bar. This way the whole thing will be more structurally integrated. So if I can just put the motor clamp in it, both sides, then putting the extrusion bar like this, then the other side goes same, and same goes for this side as well. Now connecting both the part. So the whole idea is to sliding the motor clamp inside the extrusion body. This way the whole thing is structurally more integrated, more stable. Then putting them back in this bracket. So the body at the end kind of look like this before integrating all the motors. So hopefully you can see from this idea, as you can see, this actually widens the whole area. Also then there's room for making it more longer, and also then designing more part, putting there's like a shelf here, so you can put the robotic arm and things like that. So as you can see, the concept of reverse engineering really played a crucial role. So basically that was the clamp goes to the Arduino buggy, but I reverse engineering the whole thing, whole mechanism. As you can see, this clamp supposed to go this way, but I customized it, and the best way to do this using a slide calipers. So basically with the slide calipers, then you can measure the total diameter and the screw hole size and the screws as well from the existing part. Then you do trial and error with the different CAD software, 3D printing, and eventually you get the perfect shape. As you can see, the screw hole. Now finally the assembly, as you can see, is completed. Now we can just connect the omni wheel. So this time I got a different kind of omni wheel than the drawing. These are really flexible because the slot is same size as the shaft of the TT motor. Finally, after all this hard work, the assembly, the prototype is completed. Now I will connect all the electronics and the microcontroller, including the Raspberry Pi. Let's do this. Let's do the whole assembly revision. So basically, that's what it look like after assembling, though it's not 100% finished yet. So as you can see, the reverse engineering concept worked really well. All the motors are in right position with their screws holes are aligned. Now I need to put some 3D printed other part with them. Welcome to my reverse engineering nightmare project. So basically this project actually started with the Arduino buggy. Then this was the second prototype, but as you can see, I'm struggling to accommodate all these parts on the chassis. So this is my third prototype. Now I realize that still there is a discrepancies. I still need more spaces because the battery, Raspberry Pi, motor controller, all these things need more spaces. So this is somehow working, and I have no option left but to add the Arduino chassis on top of the 3D printed robot buggy. And for the prototype purpose, as you can see, I put two 12-volt battery. They are quite heavy and very powerful. So 2000 mAh, two 12-volt battery. One of them will power Raspberry Pi independently, and the other one will power the rest, the motor controller and the servos. Now I have used the cable tie just to fasten these two batteries. Then for now I will use the cable tie to get the chassis as well. So for now I have fastened the Arduino buggy base plate with the cable tie. So just trying to get some side view. At this stage I have already soldered 4 cables to the TT motors. Now I will get my unique motor controller. Now let's talk about my DIY motor controller head. So as you can see, I use the perf board, the strip board. So from the beginning, so this is the strip board I have used with TB6612FNG motor controller to make this DIY motor controller head. So basically I have connected two motor controller TB6612FNG in parallel with this strip board. So as you can see, the strip board is fairly simple. So if you connect in one side, then you just mirror other side. Then the common pin, you just let it go, and the pin are not common, you get something sharp and that you scratch and disrupt the connection. So this is what I've done here, as you can see. And I also put a buck converter so that I can use a separate power supply for the motor controller. At this stage I have already soldered all the motors to the motor controller. As you can see, 4 cables from the 2 motor left and the 4 cables from the 2 motor right. So for now I have 2 of the buck converter. So one of them is connected with the motor controller board, and the other one's job is to power Raspberry Pi 4 in a mobile robot platform. I modified the end of the buck converter with the barrel connector. So these are 9-volt DC barrel connector. Same I did with the cable connecting from the battery. So this cable connecting from this battery, if I just connect it, as you can see, I'm getting 5.7 volt, which is kind of optimized for Raspberry Pi. On the other hand, the other battery, this battery, as you can see, this battery, the cable coming from there, if I just connect it there, so you can see I'm getting 7.3 volt, which is powering the motor controller board. Now I will power the Raspberry Pi. Hopefully nothing blows up. So as you can see, I'm having 5.7 volt here. If I just connect it with the Raspberry Pi, so you might be able to see the power LED is on. Now I turned on the mobile hotspot in my computer, and as you can see, the Raspberry Pi is detected and it is connected. I can access my little Raspberry Pi from my PC. So basically, I'm using my laptop hotspot to connect the Raspberry Pi. As you can see, the Wi-Fi is on and the Wi-Fi hotspot, the onboard hotspot, is connected with the Raspberry Pi, and the VNC viewer is connected, is helping me to get connected. For the test platform, I'm using my portable power supply just to see the fast movement of all the wheels. Let's see if the robot works. So forward movement, reverse movement, left movement, right movement. Now is the time to do outdoor trial. So I'm taking it to my hallway, and as you can see, it is working. There is some discrepancies which I need to work on to improve. Mainly the wheels are little bit loose. One of the wheel actually actually falling off, as you can see, and one of them is having difficulties in the traction, but nevertheless it is working, and these minor discrepancies I'm sure I can fix now. The next part of the project is to improve and adding more functionality like sonar sensor and IR sensor kind of thingy. Be part of this channel, like, comment, subscribe and share. I will see you at next time. Thank you very much. Welcome to Vision 360 tutorial at Indis Tech. Today I will design an Omni wheel. So at the beginning I'm starting with a new design, then a fresh sketch. First I will draw 3 circles regardless of the dimension. The middle one is the construction line. We'll draw 2 center line as well. With a midpoint. Interesting. I'm using the screen recorder that is slowing me down. So I will draw the line again. Both of them going to be the construction line. Now is the time to assign diameters. So this one gonna be 3 millimeter, quite small. 18, 24, and 60. Now for this circle, I will eliminate everything. Small mistake. This circle not supposed to be, this line supposed to be starting from here. So I have to go back. And that's gonna be 45 degrees Celsius, not Celsius, 45-degree angle. 45-degree angle. So 18, 24, and 60 is the radius. 3 millimeter. Now to eliminate all the lines. Even the circle. We will use the circular pattern to draw 4 of them. Okay, this is the frame arm, as you can see, where the roller will be connected. It is not ready yet. Now is the time to make some fillet. 3, again this one 3 millimeter. Then with the midpoint of the circle 2 millimeter. The distance between this and this should be 2 as well. Distance between this and this is gonna be 7. We'll draw a line in between, then a midpoint circle. Midpoint circle 3 millimeter. 135-degree. Another fillet of 7 millimeter. Distance between this and that 8. Distance between this circle and the center line, the construction line. Okay, the line has not been created yet, so I will create the line this time. It was deleted before. So the distance between this circle should be 23 millimeter. Okay, look like we are all set now. Constraint off, constraint visibility off, dimension visibility off, circular pattern. Before that, I need to eliminate these lines as well. With the circular pattern. Eight of them. Hopefully it will work this time. Let's see. Okay. Good news. It's working. So our omni-wheel metal flange is almost ready. 2 mm extrude. Convert it to the sheet metal. Aluminium 2 mm. Okay. Now another drawing. Okay, so 7 mm and distance 4.95 from the center of the circle. Now finish sketch. We need to go back to the sketch again. Circular pattern, center point, eight of them. No bent part, stationary side, stationary side. I need to choose this part, but somehow it's not choosing this. Not always. Like this one, not choosing. Not this one, not this one. So all of them should be 45 degree. Then we'll go for the second time. I don't know, for some reason it does not want to choose this part, so I'll go one by one. 45 degree this one, third try. Maybe this is the viewing angle or things like that, I don't know. Let's try again. No. As you can see, it does not always want to choose. I don't know why. If you know the reason, please leave it on the comment. No. Okay, working this time, so 45 degree. Okay, so this is our metal body part for the Omni wheel. We'll give it a name, which will convert from body to component. New component. Omni metal body. Not the appropriate name, but the part is working. So this is the part we have created so far. After assigning the metal property, the color look like this. The next part we will draw the roller. So new design, sketch. Both of them are construction line. The dimensions for these lines will be this is 1.5, horizontal. Okay. Now is the time to mirror this part. Mirror line. Okay. finish drawing and do a revolve. Axis, new component, give it a name, the roller. One millimeter fillet this time. Another 1 millimeter fillet. So our roller is ready. Now I will draw the roller pin here. So for the roller pin, new design again. I'm creating all the components separately, then I will assemble them. So sketch, 7.5, 1.5 extrude, new component, this time another circle, 5 millimeter, extrude, $3 extrude. No, too much. 0.5 millimeter extrude. Then sketch again. 2.975. And the last extrude, 0.8 millimeter. Name of the part is roller joint. Appearance, new sketch for the third part. This part I'm gonna do this time. So which is gonna be 32 mm. $27.5. 18 mm circle this time. Three mm extrude. And I will do 3 mm extrude here as well. -3. 15 mm circle. And 7 mm extrude. 3 mm circle this time. 5 mm cut. 3 mm chamfer. The other side of the roller. 24 mm. 45. Both of them are construction line. 3 mm circle. Same like last time, we'll eliminate this line and use circular pattern to draw 4 of them. Finish sketch and then cut all of them. So this is our connector part is ready. We will give it a name. So this is the connector part. We will draw a hole for the adapter. 3.1. 14 millimeter cut. So this is our connector is ready, and this connector, this is for the shaft. So new part, now we will use this wheel shaft, but I will draw it freshly here. .1 millimeter. New component. 14 millimeter. .9 millimeter. .85. I need to modify this. 5.6. This will be the shaft for the TT motor. -8 millimeter. Many of the dimensions I have to go back because I'm just taking real life measurement with my slide calipers. physical appearance, I will give it yellow color. With dark gold yellow. Component named GT motor shaft. So our parts are ready. Now is the time to assemble them. At the beginning of the assembly, the file needs to be saved first. To saved, so I breached the limit of my editable document. I need to make one of them uneditable. There is only 10 document, 10 external design allowed at any given time without the paid subscription. This time it should work. Give it a name. Automobile assembly. You can drag and drop file unless it is saved in this way. So the first part I will draw, I will drag this connector. Now the first thing I would do is ground this part so that it is static. As you can see, the option I choose ground. The next part is this Omni frame. I'll choose this one. Just drag and get it out from the inside the part. Then I will make it in an angle where it is possible to choose the joint. So in this case I have more better visibility. I can see some of the sketches is still visible. So I will turn the visibility off. Sketch visibility off. Now we'll copy this part and paste for the second copy. As you can see, the second copy is just pasted inside the part. So I need to take it out. So this is the optimum angle. It will help me to choose the joint feature. Okay. Now with the joint command, I'll check the center of the screw hole. Now need to flip. As you can see, it has aligned perfectly with all the four screw fixtures. Okay. Now the second one. Joint. No. flip, okay. Now as you can see, the job is almost done. Now this roller pin, same like last time, drag and drop, and make sure the parts is not inside in another part. Then get it in optimum angle. Again, we need this roller joint as well. The roller joint, you can see the sketch, so I turn off the sketch visibility. I will copy this because that need to be both sides. Flip. As you can see, just flip this side. Now the other one. Okay. So this is the current condition. Let's zoom in. Minus 0.44. So we have some clearance. We can see the joint visibility, so I will turn off the joint visibility just for better presentation. Now we will copy the pattern, copy the part in a pattern mode. So pattern, circular, not bodies. These are components. So we choose this component, roller joint second, axis. It's gonna be this axis. We need 8 of them. So as you can see, our wheel is completed. Now we will put the wheel shaft. This wheel shaft is for, it works as an adapter for the TT motor. As you can see, the TT motor shaft goes in and the other side get connected with the Omni wheel. So flip. Okay. Now to drag the TT motor. As you can see, for some reason, the location of the TT motor is far beyond. So this is the omni wheel, as you can see, barely you can see, and the TT motor is there. So if we just drag it close, that looks all right. Zoom in. We'll copy this circle with this circle. Get the part a little bit closer. Minus 0.44. I need to get it more out, so I will just edit it, edit the joint, get the better visibility. So minus 22 seems appropriate. Yes. Now I will do a presentation from design, new drawing from design. Full assembly. Okay. I did a mistake. I'm supposed to choose A2. Regardless. So I will get shaded view with northeast isometric, and the scale should be 2:1. Okay. Then the next view, let's check the projected view. It is angular, so I'll just create another base view. This time slightly bigger, 1.5:1. Seems alright. visible edges. Then print. We can print it in a PDF format. You also can change the paper size as well. So like this one is printing in A4 size paper. You can change the paper orientation as well. So I will keep it in landscape. Microsoft Print to PDF, current sheet, A4, print. So I have already done the pre-printing. So this one I will give a mechanism well. I don't know if my spelling is right or not. So I'm giving C. As you can see, the full drawing in a presentation format. You can modify this according to your need. That's all for today. I will leave the file in the comment box. So please do not forget to like, click, subscribe and share. I'll see you at next time. Thank you.